And at Raybestos, performance, quality, and reliability are a part of every product.
Hi, my name is Irvin Gers. We here at Raybestos Powertrain manufacture a wide variety of products for automotive OE and the aftermarket. At the core of our business is our wet friction materials. These are used in a wide variety of applications ranging from automotive street to high-performance drag racing, agricultural to heavy duty. Most of our manufacturing efforts and processes are used to bond friction material to a steel core. It's very similar to this. We've been doing this for over 100 years now, and we'd like to consider ourselves experts in our field. We are the only vertically integrated manufacturer that can make our base paper, we can resin saturate, we can blank out steel cores, we can formulate our own adhesives, and bond and size in-house. Today, I want to talk to you about a different type of Raybestos Powertrain product. These here are some samples of our Raybestos Powertrain lockup torque converter rings. We manufacture the base paper material, we resin saturate, and we adhesive coat. The difference is you, the customer, will do the bonding. Naturally, we want you to recreate the same success in bonding that we do here at our facility. This video will illustrate proper bonding procedures beginning with target specifications and then moving on to key elements of correct surface prep for bonding. Remember, Raybestos Powertrain torque converter rings come to you pre-coated with our latest adhesive, Quicker Bond, which is designed to reduce bond time, and there is no need to add more adhesive if you follow the instructions. There are two types of bonds I'd like to discuss with you. One of those is a mechanical bond, and the other one is a chemical bond. A chemical bond is achieved by using an agent such as a glue or an adhesive to attach two items together. Such as if I was to put a glue or an adhesive on my hands and I was to press them together, that would be a chemical bond. Mechanical bond is where the two objects are physically interlocked, such as this. What we want to achieve is a chemical bond and a mechanical bond, and that would be where we not only get the chemical bond between the two objects, we also want them to interlock. That is a strong, solid bond that is both chemical and mechanical. And that's what we'll be working on today. We'll show you how to properly prepare the bonding surface so that you can achieve that successful chemical and mechanical bond. So let's head over to Ray's garage. Welcome to Ray's garage. Today, before we get started, I'd like to talk to you about safety. Work area safety is very important. And one of the things that I'd like to do is I like to wear protective clothing like a lab coat, safety glasses, protective gloves, nitrile gloves for when you're working with chemicals, thermal gloves for when you're working with hot objects, and a respirator to make sure that you're breathing clean air. Surface finish is very important. If you have an incorrect surface finish, you will not achieve a successful mechanical bond. For our surface finish, we are looking for a target of 120 microinches, and with a variance of 100 microinches to 140 microinches. So as you can see here, we've already prepared our surface. There's a number of ways you can do this, but primarily the most common ways of preparing the surface is either to turn it on a lathe or to use a grit blast. So we've got our pocket surf set up. You want to have it set to measure about 180 thousandths with a 30 thousandths cutoff. It's as easy as pushing a button, you get your reading, and we're good to go. In some designs, pistons can be tapered on one side or on both sides. If the piston is flat, the platens should be flat. If the piston is tapered, the platens should match the taper. If you do not make allowances for tapered components, your bond will fail. For example, if the platens only contact the inner diameter of the torque converter ring, expect low adhesive shear strength on the outer diameter. If the platens only contact the outer diameter of the torque converter ring, expect low adhesive shear strength on the inner diameter. We're going to do a time and temperature study. We want to make sure we set our bonder up for the optimum bond and that we don't have any problems with it. A critical component of the bonding process is the calculation of the net facing pressure, which is required to create a successful bond on each particular piston or damper assembly. If you don't have access to a bond pressure calculator, here are the calculations you'll need to perform. First, determine the surface area of your torque converter ring. This basically involves determining the surface area of two circles, the outer diameter, or the OD, and the inner diameter, or the ID, of the torque converter ring, and subtracting the smaller number from the larger. Your formula should look like this. Pi times the outer diameter divided by 2 squared minus pi times the inner diameter divided by 2 squared equals the surface area. Next, we take the net facing pressure we want, a figure between 200 and 250 psi, and multiply that by the surface area we just calculated. Then, divide the area of the piston, which is calculated by pi times the piston diameter divided by 2 squared. And that totals our air pressure needed. The formula will look like this. So our two formulas will look like this. Keep in mind that every shop environment is different. You may have to choose a higher or lower net facing pressure depending on the equipment that you use. Just make sure your net facing pressure stays between that critical range of 200 psi and 250 psi. You can also find these formulas under Tech Tips on the Raybestos Powertrain website at www.raybestospowertrain.com. So now what we're going to do is we're going to do a time and temperature study, and the reason why we're doing this is we want to make sure we set our bonder up for the optimum bond, and that way we don't have any problems with it. So one of the first things that you want to do is you want to preheat the bonder so that way it takes less time for the bonding process to occur. So I'm going to turn the power on. Notice the different readings here. The lower reading in red is the temperature that we want the platen at. So this is the upper platen, we want that at 450. The lower platen, we want that at 450. So in order to speed up the heating process, I'm going to lower the ram, and that will get rid of the air that's in between the two platens, and it will aid in the heating process for the platens. While we're doing that, we want to make sure that we've got the right amount of air pressure on our ram, and we do that by what we discussed earlier, which is we go through our formulas and we determine how much air pressure we need. Well, we've already measured this ring, and this one here is 9.875 inches, and the inside diameter is 8.75 inches. So with all those calculations, what we were able to determine is that we need 120 psi on our 6-inch ram to do the bonding that we need in order to get the proper amount of net facing pressure. For our temperature study, what we're going to do is we're going to put our temperature probe on our assembly, and we're going to put a blank ring on top of it. And the idea is you want to make sure that when you lay this on here in between, that the end of the temperature probe will be about the center of the torque ring. Not necessarily in the center here, because as you can see, that may just catch the very edge of that. So just kind of get it in there. And you want to use something to hold it in place. You can use a thermal tape of some kind to hold the wires, but do not cover the end of that tip there, because that's going to sense the temperature as it rises as we're doing our study. Okay, now that we got our temperature up where we want it, we're going to have my assistant Dan go ahead and put our piece into the bonder. So while he's doing that, I'm getting ready to set our stopwatch. And what we want to do is we want to time how long does it take for the bond line temperature to reach our 350 degrees. That's very important that we know how long it takes for that to happen. Okay, so you may want to do this a couple of times on each new item that you're doing this on, so that you get an idea of what the average time it takes for this assembly to get up to the bond line temperature that we're looking for. We also know that by our temperature study, it took approximately 54 seconds, between 53 and 54 seconds, for a bond line temperature to get up to 350 degrees. So what we'll do is, when we go to bond our part, we will put it in for 53 to 54 seconds and then add 2 minutes, and we should have a good bond. Okay, we're going to talk about surface prep now. Surface prep is very important. If you don't have a good clean surface with the proper finish on it, you're not going to achieve a successful bond. And that's the whole point of this video, is to show you how to do that. So here we have our damper assembly, and we're going to just go with the assumption that you just took it out of your parts cleaner. There are a variety of parts cleaners. There's hot parts washers, there's other methods. So we're not going to get into what you're going to use for that. But once you get it out of there, you want to make sure there's no residues left over. You might even take it to a solvent tank and wash it off to get all the cleaning debris from your parts washer out of there. But solvents are not a good cleaning agent as far as what we want for surface prep. They contain fluids such as oils and other contaminants that are floating around inside that tank. So you can use solvents, but that's not the final prep. What we're going to talk about is you can use rubbing alcohol as long as it has 10% or less of water in it. You can use ethanol, same type of setup, less than 10% of water. Or you can use a chemical that we use sometimes, which is MEK. Also, do not use a shop rag. I know it's the easiest thing in the world to do. You've got one on you, you clean your hands with it, but before you grab that rag and you go over this like that, these will leave lint behind, and you do not want to do that. Even if you can't see it, there is lint there. So the best thing to use is a lint-free cloth, such as one that I have here. So what we're going to do is we're going to put a little bit of this cleaning agent on there, and then we're going to go around this, clean all of those oils and other nasty things that are on there. And then you can take a dry one, just wipe that down, make sure everything's nice and clean, and we're ready to bond. Now we want to make sure that when we go to put this in the bonder that it's going to stay in place. So I could put it like that, and if I handle it, it'll move around. So what I'm going to do is I'm going to take a little bit of this MEK, and I'm going to put it in a couple of places here. And what that's going to do is that's going to kind of soften that adhesive just a little bit. And we hold it in place for a few seconds or so. And what it's going to do is it's going to make it tacky enough, as you can see. That ring is in place. It's not bonded yet, but it will stay in place while we put it in the bonder. We've got our bonder already preheated now. As you can see, the upper and lower platens are at least 450 degrees. So we are ready to bond. Let's raise the upper platen. And Dan is going to put our piston in there, and we're going to go ahead and bond. Now when you're doing this, make sure that you get that piston or the damper assembly centered on the platen. That way we make sure we get good coverage when the upper platen comes down. Keep in mind that this assembly is very hot, so you want to make sure you're wearing your protective gloves. And we'll let it cool off, and then we'll do some checks to make sure we got a good bond. After we pull the assembly out of the bonder, one of the first things we want to do is a preliminary test, which is an air test. And basically the idea behind this is you take the air nozzle and you want to blow air between the ring and the assembly and see, does the ring just pop right off? So once it passes that test, then another test that you can also perform is one that we don't want this to be a destructive test, but it's called the knife test. And we're going to take a blade, a dull blade of some kind, and gently go around the outside ring and see, does the ring want to pop right off of there? And as you can see, our ring has stayed on the assembly. So another test, and this one's going to be a little bit more on the destructive side, is the chisel test. And the idea of this one is we're actually going to take a dull chisel and we're going to run it at about a 45-degree angle, and we're actually going to cut the ring. And what we're looking for is what's underneath the surface there. Does the adhesive look like it has adhered to the assembly, as well as also the underneath side of the torque ring. And as you can see, it looks like we've got a good bond. As a last resort, we're going to do what is called a bend test. The bend test basically is taking a section of the bonded assembly that we're going to cut out, and we're going to bend it over a 1-inch rod. And the idea is what happens to that friction material after we bend it. And that's why this is a destructive test, because we do have to cut a piece of the assembly out. So, as you can see, we are now starting to perform the test. And we are going to actually bend this down as far as it will go in this assembly. And as we can see, we're already getting something happening here with the material. It's splitting. Well, we want it to do that. What we're looking for is what does the underneath surface between the bonded assembly and the piston look like. So as you can see, we have a good bond here. We still have adhesive that is bonded to the metal part of our assembly. We still have some friction material in the adhesive, and we have the split, which is what we were looking for. So this will pass the bend test. So there you have it. We've had a successful bond. In order to achieve that successful bond, we've talked about surface finish. We've talked about time and temperature study, which we use to set the bonder up properly. We've talked about surface cleaning, and we've also talked about testing in order to ensure that we have had a successful bond. If you'd like to know more about Raybestos Powertrain, please feel free to visit us on our website at raybestospowertrain.com.
And at Raybestos, performance, quality, and reliability are a part of every product.